Sections 7, 8, and 9 are a discussion of bases and salts, weak bases and salts. So weak bases are substances that remove protons from other substances. They react with water to produce hydroxide in most cases, but that doesn't always have to be the situation. You can have a Kb base dissociation constant just like you did for acids, and it's calculated the same way, reactants over products, concentrations of reactants over products. And we have a list of Kbs in the book. We can calculate the pH of a basic solution. If you know the acidic pH, you can use the Kb. If you know the Kb or can calculate the Kb, you can get the pH. Very similarly to how you get the acid pH. Ka and Kb are related. If you know the Kw, which is 1.0 times 10 to the negative 14, we saw that earlier, then you can calculate A or B if the other is known. Anions are also bases. So since they have basic properties, they can react in a hydrolysis reaction to form OH and conjugate acids. And cations behave like acids, so they're acidic protons. Metal cations are a good example. They will lower pH of solution. So how do cations and anions affect solutions? An anion that is the conjugate base of a strong acid will not have an effect on the pH. It's just too weak. An anion that is the conjugate base of a weak acid will increase pH. Of course, we know bases increase pH and move them toward 14. A cation that is the conjugate acid of a weak base will decrease pH. Of course, acids will decrease pH, so we know that. Cations of strong Arrhenius bases do not have an effect on pH. Metal ions decrease pH, making the solution more acidic. And when a solution contains both the conjugate base of a weak acid and the conjugate acid of a weak base, the effect on pH depends on Ka and Kb, so whichever is stronger. Things that affect acid strength are polarity of the hydrogen bond. So we know acidity increases from left to right across a row of the periodic table, and it also increases from top to bottom as you move down a group. In oxyacids, there's an OH bonded to another atom. The more electronegative the other atom, the more acidic the acid. So for oxyacids, acidity increases with the number of oxygens. As I add oxygen, my acid becomes more acidic. There is resonance in some conjugate bases of carboxylic acids, and that stabilizes the base and makes the conjugate acid more acidic. So let's look at a few examples. Example 15 is on page 691 in the textbook. Calculate the concentration of hydroxide in a 0.15 molar solution of ammonia. So if we know that our concentration of ammonia is 0.15, we can look up the Kb for this reaction and find that it is 1.8 times 10 to the negative 5 for ammonia. And our reaction is that ammonia when placed in water, becomes ammonium ion and hydroxide ion. So our Kb expression will be the concentration of ammonium times the concentration of hydroxide over the concentration of ammonia. And we're given our Kb value 1.8 times 10 to the negative 5. We don't know ammonium and we don't know hydroxide, but we are given ammonia, which is 0.15. So when we work that out, we can replace ammonium and hydroxide with X, multiply Kb times the concentration of ammonia, and we find that X squared is equal to 2.7 times 10 to the negative 6 molar. And when we take the square root, X, which is the concentration of OH, and also the concentration of ammonium, has a value of 1.64 times 10 to the negative 3 molar. For the practice exercise 415, on page 692, which of the following compounds should produce the highest pH as a 0.05 molar solution? Pyridine, methylamine, or nitrous acid? So when we work this one out, we have pyridine, methylamine, and nitrous acid. And formulas: C5H5N, CH3, NH2, and HNO2. The Kb values for these are 1.7 times 10 to the negative 9, 4.4 times 10 to the negative 4, and nitrous acid actually has a Ka of 4.5 times 10 to the negative 4, and when we use Kw, we can find that the Kb for that is 2.22 times 10 to the negative 11. So our highest Kb is methylamine, and that would give us the most hydroxide. Sample 1616 is on page 692. A solution made by adding solid sodium hypochlorite to enough water to make 2 liters of solution has a pH of 10.50. Using the information in equation 1637, calculate the number of moles of sodium hypochlorite that were added to the water. So let's look at what we know. We know that pH is 10.50 10.5. So we can find a pOH by saying 14 minus the pH. So 14 minus 10.5 gives us a pOH of 3.5. From that pOH, we can find the hydroxide concentration. So if we know our pOH is 3.5, we can do an anti-log calculation and find that our concentration of OH is 3.16 times 10 to the negative 4 molar. Since we have our hydroxide concentration, we can use Kb. The Kb expression for, we need the equation first. We have ammonia in water, and we get ammonium ion and hydroxide ion. Our Kb expression is the concentration of ammonium ion I'm sorry, I'm doing the wrong problem. Okay, we have a Ka and a Kb for this problem already. We have a Ka of 3 times 10 to the negative 8, and we have a Kb of 3.33 times 10 to the negative 7. Our equation is NaClO combined with water gives us sodium hydroxide and HClO. So from that, our Kb expression will be the concentration of HClO negative times the concentration of hydroxide over the concentration of ammonia of ClO. I keep looking at the wrong problem. So if our Kb is 3.33 times 10 to the negative 7, and we found that our OH concentration was 3.16 times 10 to the minus 4. So we fill that in for HClO and for OH. And we can get our concentration for ClO minus. And we find that to be 0.30 molar. Sample 16.7 is on page 695. Calculate the base dissociation constant Kb for the fluoride ion, the acid dissociation constant Ka for the ammonium ion. So the Kb for fluoride ion is Kw over the Ka of hydrofluoric acid. Kw is 1 times 10 to the negative 14, and you can look in Appendix D of the textbook and find that the Ka of hydrofluoric acid is 6.8 times 10 to the negative 4. And when you work that out, you find that Kb of fluoride ion is 1.47 times 10 to the negative 11. Part B wants the Ka of ammonium ion, which is Kw over the Kb for ammonia. Kw again, 1 times 10 to the negative 14. And Ka is 1.8 times 10 to the negative 5. Again, this is in Appendix D. And we get 5.56 times 10 to the negative 10. Sample 18 is on page 698. Determine whether aqueous solutions of each of the following salts will be acidic, basic, or neutral. So for 18, we are given barium acetate, ammonium chloride, CH3NH3Br, potassium nitrate, and AlClO4 3. We can make conjugates with these, so we would end up with barium hydroxide and acetic acid, ammonia, and hydrochloric acid, CH3NH2, and hydrobromic acid, potassium hydroxide, and nitric acid, and aluminum hydroxide, and HClO4. Go through and determine which are weak and which are strong, and what we find is A is basic, B is acidic. Whichever one is the strong one is going to determine the acidity or basicity of your solution. C is acidic. D is neutral. And E is acidic. Sample exercise 19 is also on page 698. Predict whether the salt Na2HPO4 will form an acidic solution or a basic solution on dissolving in water. So we have Na2HPO4. If we take our HPO4 with a negative charge, and dissociate it, we get hydrogen. Ion and phosphate ion. And then if we place it, that would be acting as an acid, acting as a base in water. It would produce H2PO4 minus and hydroxide ion. And you can find Ka's and Kb's for HPO4. The Ka is 6.2 times 10 to the negative 8. And for H2PO4, excuse me, that was a Kb, you have 7.5 times 10 to the negative 3. So we can do K expressions for them. For PO4, 3 minus, we can find Kb by saying Kw over the Ka for HPO4, 2 minus. And to get a Ka for HPO4, 2 minus, we can use Kw and the Kb of H2PO4. So when we put our numbers in, KbPO4 is 1 times 10 to the negative 14 over 6.2 times 10 to the negative 8. And that gives us 1.61 times 10 to the negative 7. Our Ka is 1 times 10 to the negative 14 over 7.5 times 10 to the negative 3. And that gives us 1.3 times 10 to the negative 12. Our Kb is much larger than our Ka, so our solution is basic. And then our final sample problem, sample exercise 1620, is on page 702. Arrange the compounds in each of the following series in order of increasing acid strength. So we have AsH3, Hi, NaH, H2O for part A, and for part B, H2SO4, H2SeO3, H2SeO4. If we get electronegativity differences between the elements, what we have for AsH3 is 0.1, for Hi is 0.4, for NaH 1.2, and for H2O 1.4. Putting these in order of their electronegativities, then we have our metal NaH, then AsH3, then H2O, and Hi. And then our second example, H2SeO3, H2SeO4 and H2SO4 are in the same, the Se and the S are in the same group. So our H2SeO3 has the least oxygens. This is oxyacids. And then S is more electronegative than Se. So then H2SeO4 and H2SO4.
Ms. Paul, do you have one?